Good afternoon, everyone, and welcome to the second webinar in our Galileo Webinar Series. My name is Carline Amsing, and I'm joining you today on behalf of Geo-informatie Nederland, or GIN as we call it. We are very pleased to organize this webinar together with the European Union Agency for the Space Program, EUSPA, and the Netherlands Space Agency. A warm welcome to everyone joining us today. It is great to see both familiar faces from last week's introductory webinar and new participants who are joining us for this more technical session.
Це в мене стартанув. 16 година. Добре, Кіцун, давай буду слухати. Давай, цілую, давай.
Just to start, maybe everyone can mute their microphone during the presentations. Thank you. Well, last week we introduced the Galileo and the high accuracy service, explored the fundamentals of the system, and discussed a number of practical user applications. Today we will take the next step by looking in more detail at the technical aspects of Galileo's high accuracy service, or HAS, and the open service navigation message authentication, better known as OSNMA. These services are becoming increasingly relevant as the demand for accurate, reliable, and secure positioning continues to grow across many sectors, including surveying, infrastructure, mobility, autonomous systems, and many other geo-information applications. Our aim today is to provide you with a deeper understanding of how these services work, how they can be implemented in practice, and what the opportunities are they offer for developers, system integrators, and professional users. I'll go to the agenda. Well, let's walk through today's program. It's quite full. First, Thomas Bleker and Marcus Arup from the Netherlands Space Agency will introduce the role of the Netherlands Space Agency in satellite navigation and its contribution to Galileo and innovation within the Dutch and European space ecosystem. They will also be joined by Tomme van der Wal from Aerovision, which is a company in the Netherlands, and Bas van der Hoeve from CGI, who will briefly share their practical experiences with OSNMA and the Public Regulated Service, or PRS. After that, Martin Damhuis from the Ministry of Infrastructure and Water Management will present the Netherlands' new navigation policy, highlighting its strategic priorities and societal relevance. And next, we are pleased to welcome Teresa Martinez and Emilio Gonzalez from EUSPA's GNSS Service Center. They will provide an in-depth session on Galileo, HAS, and OSNMA, covering service performance, implementation aspects, and examples of HAS and OSNMA-enabled receivers in real-world applications. And finally, we will conclude with a presentation from the Galileo Reference Center. Peter Buist and Axel van den Berg will introduce the role of the Galileo Reference Center and present the latest performance results for both HAS and OSNMA, including key service indicators and achievements. Well, before we start, a few practical remarks. As just mentioned, please keep your microphone muted during the presentations. Feel free to submit any questions throughout the webinar in the chat. We will reserve some time after every presentation for questions and discussion. This webinar is being recorded and will be made available afterwards for those who would like to watch it again or share it with colleagues. Before we dive into today's topic, I'm going to take a brief moment of your time to introduce our association, if you're not already familiar with it. We are Geo-informatie Netherlands. We're organizing this webinar. At GIN, we bring together professionals from across the entire geo-information domain in the Netherlands. Our community includes people from government, academia, industry, and consultancy, all working with geospatial information in different ways. What makes GIN unique is three things. First, we have a broad focus on geoinformation. We connect disciplines and sectors because many of today's challenges require collaboration across the entire geospatial ecosystem. Second, we have an independent position. As an association, we act as a neutral platform. where knowledge can be shared openly and where organizations and professionals can connect and learn from each other. And third, we have quite some deeply engaged members. Our strength lies in our active community, people who are curious, willing to share knowledge, and eager to explore new developments and innovations. And this slide really captures why we exist. We believe that geoinformation is essential for creating a safe and sustainable and livable environment. Whether we're addressing challenges related to climate adaptation, infrastructure, mobility, energy transition, or spatial planning, geoinformation remains to play a crucial role. And behind all of that are the geoprofessionals who collect, analyze, and apply this information. And your expertise is more important than ever. As an independent association, our role is to bring the professionals together, promote the use of geoinformation, and support the continuous development of knowledge and expertise within our community. By doing so, we contribute to the effective use of geoinformation in tackling the major spatial challenges facing the Netherlands today and in the future. And that is exactly why topics such as satellite navigation and high accuracy positioning matter. They are becoming increasingly important building blocks for the geoinformation solutions of tomorrow. A big part of our work is organizing events. Oh, that was a bit too fast. Throughout the year, we organize conferences, lectures, symposia, excursions, etc. Opportunities to learn and share knowledge and connect across our community. And today's webinar is one example of bringing the community together around emerging topics. Another example is our magazine, an important way of sharing knowledge. It features articles, reports on developments in the Dutch geoinformation sector. Well, behind all of these activities is a team, a 7-member board, and myself as the association director. Together, we work to keep connected, active, and relevant for our members and the wider geoinformation community. So finally, a call to join for a stronger profession. If you're not already a member of GIN, we would like to invite you to visit our website and consider becoming a member. You become part of an active network of geoprofessionals and help support initiatives like today's webinar, which is organized by and for our members. So now I would like to give the floor to our co-organizer, EUSPA. Carmen Aguilera will give a short introduction as well. Carmen, the floor is yours.
Thank you and good afternoon to everyone also from my side. It is a pleasure to see so many participants in this second webinar, so thank you for joining. I will just take a few minutes to also welcome you from the side of EUSPA to this webinar and give you some additional information. So just as a reminder, just a confirmation, can you see my screen?
Yes.
It is working. Thank you very much for the confirmation. Just as a reminder on the U-Space program, as I already anticipated during the previous webinar, the U-Space program 2021-2027 puts all the U-Space activities under one umbrella. Today we will be focusing on the Galileo services, but we wanted to give you the broader picture to possibly also get your interest on other space programs. As I said, today we will focus on Galileo, our global satellite navigation and positioning system. And if interested, we can also continue in other occasions looking at Copernicus, the Earth Observation Program, GovSatcom and IRIS Square, which are the initiatives of the Union on providing secure connectivity and space situational awareness. In this framework, the role of EUSPA, as anticipated in the previous webinar, is to provide exploitation with the different level of activities depending on the program, ensure secure operations, and facilitate the use of the space programs. We like showing this map to explain that we are a multi-site agency. Our headquarters are located in Prague, but we also have sites in other countries in the EU. In particular, in the case of the Netherlands, we have the Galileo Reference Center. So in case that you will know and understand that the role later during the webinar, and in case you wanted to exchange more details on the use of Galileo and EGNSS services, or you wanted to get a more practical information, probably it will be easier to visit Peter and Axel, who are based in Noordwijk. From the Galileo Service Center, that will be also part of the webinar. In the Galileo Service Center, we are focusing on providing services to the users and interfacing the users and providing practical support. And we just wanted to introduce some numbers and some factors, because today we will focus on the practical use of receivers, how to develop applications with Galileo high accuracy, with the OSNMA, how to configure receivers, and we wanted to draw your attention to information that is already available in the GFC website, where we are listing all the receivers that are already commercially available in the market and that are integrating Galileo high accuracy, Galileo SNMA receivers capabilities. So in case you are interested in using one of these receivers in your activities, you can use this information as a reference to choose the right one for your application. You can see here some pictures. So we have some of these receivers available also in the Galileo Service Center, in the Galileo Reference Center. So in case you want to understand a bit more on how they work, we can also show them to you and help you to use them from our sites. Just to inform that this webinar is part of a series of vertical webinars that we perform usually to explain the users on what is the best way to use EGNOS, Galileo, and in particular HASO and OSNMA in the different applications. Here you can see a photo of a webinar that we did last year in the Galileo Reference Center. And we continue repeating this activity in different locations. In case you are interested in getting support on how to configure a receiver, how to use it, or even run a testing campaign with one of these receivers in your application, let us know. We will be happy to assist you and help you to understand which performances you can get for your application. And I would like to finish with an invitation to another event, which is the user consultation platform that we are organizing by the end of November, 26th, 27th of November in Prague. It will be a 2-day event where we will discuss with the users from the different areas of applications on the needs, requirements that users may have for the space components. In particular, what we want to understand from users like you and users in other domains is how well or badly are the current space services meeting your needs, and if we should evolve them in a certain way so that you can make a better use of these services. Normally, this event is hybrid. We do encourage you to come in person, but in case you prefer to join remotely, we will open soon the registration, and you will be able to participate remotely as well. And thank you very much again for your participation in this workshop. I see the participation increasing and increasing, so it is a pleasure to have such a high interest on the use space services. Thank you very much.
Thank you, Carmen. I will now share the slides from NLSA, and Marcus can take the floor.
Great. Good afternoon, everyone. Can you hear me okay?
Yes.
Perfect. So quick introduction. I wasn't here last week. My name is Marcus Arup. I'm the new PNT advisor for the Netherlands Space Agency. And we have Thomas Blaker, my colleague here as well, to help field questions. So if we go to the second slide already. For those of us who were here last week, this might look a little familiar, so I'm going to run through them a little bit quicker, but a little bit of as the space agency, we act as the Dutch government's space body to develop and execute our national long-term space goals. We do this with a societal focus to leverage space technology to solve terrestrial challenges in mainly climate, agriculture, mobility, and security, but also other fields. We focus on connecting government bodies, knowledge institutions, and industry together to create a robust and resilient space sector with the end goal of maximizing economic and societal return on Dutch investments into space infrastructure. Next slide, please. So quick summary of the European space ecosystem and our role in it. One of the biggest ones here is, of course, our partnership with the European Space Agency and hosting ESTEC in Noordwijk. We also have the EU Space Program, EUSPA, where we collaborate closely with them and the European Union to help shape policy and programs representing Dutch interests. In global positioning, we promote Dutch expertise in international consortia and facilitate global trade missions, including those being central for international and national space affairs. And we do this with a big focus on strategic autonomy, of course, with current developments that we work with European partners to ensure independent, reliable access to space data and services. Next slide, please. So the European Space Agency's Navigation, Innovation and Support Program, NAVISP, and the Netherlands Space Agency collaborate to foster innovation in satellite navigation by funding advanced PNT, that's positioning, navigation, and timing technologies. Through three key elements, NAVISP offers competitive funding, while NSA facilitates access to these resources to support Dutch industry and research initiatives. NAVISP is composed of three elements. Element 1 focuses on innovative PNT concepts and feasibility studies. Element 2 enhances competitiveness of commercial products through co-funding, and Element 3 supports national PNT strategies and institutional needs. These elements are designed to foster, enhance, and support European PNT industry across different stages of development. And right now, the Netherlands is mainly focused on Element 2 and 3. Next slide, please. So strategic priorities in positioning, timing, and navigation. So what the Netherlands Space Agency does is that we guide the government of the Netherlands on GNSS for strategies and dependencies, highlighting where things are going well, where they aren't going well, what we can do. We do this to, again, build resilience, highlighting critical nature of PNT data for all vital national infrastructure, such as telecom, energy grids, or more. We do our best to showcase Dutch expertise in receiver technology, signal processing, and secure navigation, and we do this again to future-proof. Next slide, please. So, of course, one of the key points is here, Galileo. So that's European GNSS as a highlight. We focus on development and deployment. So we support Dutch scientific and industrial contributions to the Galileo constellation. Mainly two big points that we have here are the Bonaire Galileo Service Station and the Galileo Reference Center, which we'll be speaking today. And Galileo offers a broad range of services, not to just mention the high accuracy service, different authentication services, and a constant focus on the evolution and development of the Galileo constellation to have second generation Galileo. Next slide, please. To run through our couple different services, some of these will also be covered by other speakers, so I'll go a little bit faster through those, but the open service, OS, is Galileo's core service. It's free, globally available, and received by most Galileo-ready devices. It offers higher accuracy than the standard GPS open service, and includes different subservices such as ranging, distance to satellites, positioning, and timing. CGI, one of our co-speakers, will also cover PRS, so I'll go pretty quick through that, but in essential, it is a secure government service which offers the really best-in-class high interference resistance, and remote access control to make sure that your data gets to where it needs to go, you know who gets it, and how it's handled. Next slide, please. The high accuracy service will also be covered by the Galileo Service Center. So again, key points here are that it is utilizing real-time orbit and clock corrections by the E6 satellites to receive and achieve faster performance in Europe compared to global level. It is free, it's compatible with GPS, and offers improved precision, though it requires an initial time to fix of several minutes. Search and rescue is another service offered. This allows users to transmit distress signals and locations during emergencies. Uniquely it is the only Galileo service where signals travel from the user to the satellite. It picks up beacon signals, relaying them unaltered via a forward link to ground terminals and local rescue services, often locating users within 1 kilometer and up to 90% of cases so far. The system also features a return link option, which sends a receipt of confirmation back to the user, knowing help is on the way. Globally available, but optimized for Europe and the North Atlantic, SAR is essential for maritime, aviation, and remote land services where cellular coverage is often unreliable or unavailable. It is currently used by the Netherlands Coast Guard, and the Netherlands recently had a live demonstration of this in Bonaire in collaboration with the European Space Agency. No, sorry, JOSPA. Next slide, please. So here for the Open Service Navigation Message Authentication Service, we also have Tommy from AirVision to speak on this for their experiences, and we also have the GNSS Service Center for in-depth. But ONSMA authenticates data transmitted by the Galileo satellites, proving the signal genuinely originates from its constellation. While accessible to private parties and simpler to implement than PRS, it operates with a few minutes of delay and offers slower security. It does not authenticate final location coordinates, making it ideal for non-critical commercial uses such as smart tachographs, logistics, and agricultural monitoring. The Emergency Warning Satellite Service, EWSS, is a new service under development that transmits alerts via satellite for a wide range of impending disasters. Authorized national agencies draft an alert, classifying the threat type, severity, duration, using standardized formats to specify target areas. This standardized message is then broadcast through navigation satellites and can be received by standard GNSS hardware, including almost all modern smartphones. If the receiving device uses its own location to determine whether it's within the target zone, it will then get the alert. EWSS covers various threats like fires, environmental issues, geological events, health crises, and severe weather, traffic disruptions, and attacks. It covers any need you might have. It is a crucial redundancy layer along with local sirens or mobile networks, such as the Dutch NL Alert, remaining fully operational even if local power or telecommunications fail. That takes me to the end of my quick overview of the different services. Then if you go to the next slide, I'll thank you for your attention, and I will hand off to our co-speakers. Thank you.
Hi, good afternoon, everyone. My name is Bas van Hoeven. I'm here with a colleague, Nick, who has the patent on this slide, actually. So thanks for that. Brief introduction on PRS, Public Regulated Service, which is the encrypted signal of the Galileo service, makes it unique since it's a public signal and not for military purpose only. It is therefore controlled, so it has access management on the signal layer, let's say. So we can decide who has access, who can't have access granted, and that's based on policy making as well, and compliancy, of course, to European regulation. So that's in core what it is. And it provides an encrypted signal, and thus it's providing confidentiality, integrity, and authentication of the signal. That's what it does, and therefore we are better resistant against spoofing, meaning that that's misleading information, right? So pretending that a receiver is somewhere else than reality, or jamming. It's better resistant against jamming because it's dual frequency that we are receiving the signal. So you need quite a big jammer in order to jam the full spectrum here. And that makes it better resistant. And jamming is that you basically create a lot of noise and therefore you don't receive the signal anymore, in short. So if you look at PRS, the Power Regulated Service, the way you can receive it as a user, we created two kind of solutions there. You have the real-time receiver, as we all know it from the TomTom in the past and what is in your car for navigation purpose, but also for timing purpose. Of course, don't underestimate the importance of timing. That is part of those satellite navigation signals because they are also encrypted here, of course, so more secure. And the real-time is as we know it, but it has a lot of complexity in the receiver because it's cryptography, of course, that is required in order to be able to read the signal and understand the signal. And then we also created, and that's on the right hand side here, the PRS tracking, if you like, which is kind of snapshot technology or remote server as it's called as well. And there what we do is we capture a bit of the snap of the real time signal from Galileo PRS. We record that, and then based on a couple of milliseconds we are capable of using the PRS signal, the position of that where that snapshot has been taken. And that's of course a different use case because it's not real time, it's near real time. But you can use it for enforcement purpose, inspection purpose, tracking and tracing of valuable goods with a kind of delay, but you're quite sure about the location then. So it's not just authentication, you also have the real position available in that signal. And it makes it less of a burden on the security side because the cryptography is on a remote, resides in a remote centralized system, which can be in a safe environment, let's say secure environment. So that's a way of using the signal. And what we used to do is, there's a question. I can't process two things at the same time. I'm sorry for that. But let me finish the last bit, and that's that we do with support from the Ministry of Infrastructure and Water Management. So Martin is the next speaker, I think, after Tomme, but also with the NLSA, so Thomas and Marcus. We also did some experiments in the past in real-life cases, I would say, so really integrating PRS in existing tracking and tracing solutions in various means in the Netherlands for emergency services, but also for more administrative purpose, manure, which is the cow shit in the Netherlands, to follow that when we take a snapshot when it's loaded and offloaded the manure, because that's a lot of fraud going on there from an economic value. And we experimented a lot there with PRS. So we can show it because the signal is there. We are able to decrypt the signal as well and show PRS as such. And that's what we do in short. Shall I take the question or do we prefer to the later?
Yes, maybe shortly answer the question.
The question, then I open the question. Is it possible to receive the water to test PRS? Yeah, you can. Yeah, so as I just mentioned, we can do the PRS processing, so we can capture the snapshots and then process the PRS signal out of that, if you want. So we can be in contact if you like, and then we can set up something. It's rather easy to do. The signal is there, the means are there, and the will is there. So open to do.
Thank you.
More questions? Otherwise, I hand it over to Tomme.
Let's hand over to Tomme. Yeah?
Okay.
Thank you.
Thank you.
Good afternoon, Tomme van der Wal. I'm in a car on my way to Brussels. I'm just diving into a tunnel, so I hope the connection will remain. I'm not driving myself, so don't be careful. Before I'll take you through this diagram, let me explain a little bit. Our consulting to users of geospatial technology. So we're not developing the technology. We're not providers of technology, but we have our customers are users of technology, and we help them make better or more innovative use of that. And we won a project, which is the logo on the right, which is funded by EUSPA. Normally I have a full slide deck with all the proper acknowledgements, but in this one slide it's just the logo. But it's funded by EUSPA, and it's also basically it's a downstream activity. So what we say is that we see a lot of use of geospatial data in agriculture, and the manure case from Bas is of course a great example. But we also see that these data from tracks, from machinery, for instance, is now used more and more to share with other people to show compliance with regulations. But these tracks are basically ASCII files. They are very human readable files and manipulable. So it's difficult to have trust in the truthfulness of these files. So therefore we are very happy and pleased that we now have OSNMA, because that can help us to show that the tracks that we produce with machinery are actually genuine and not false or manipulated. So let me guide you through this diagram. It's basically it's a data flow diagram for field activity for the arable farmer. So on the left you see all kinds of data sources, satellite imagery of course, but can also be other sources. These sources are then transferred through algorithms into what we call a prescription map. For instance, a satellite image can show where the crop needs more or less fertilizer, and that we can translate that into a prescription map. On this spot you give more, on this spot you give less. Then this prescription map is translated into a task map. Specifics of the machinery, and the size of the fields, etc. in it. And this map is a controller board of a tractor or a self-driving machine. And then the result of that is what we call the as-applied map. So that is using this task map that comes from maybe satellite imagery or other sources in combination with the GNSS location of the machine. And then it can say, yes, I did this activity on this spot. And as I said, these as-applied maps are basically ASCII files. So we use the OSNMA to increase the trustworthiness of these files. And there are two main reasons why we do this. First of all, we see more and more machinery is now autonomous or self-driving, so without a driver, robots and other equipment. So it's very important that that we can track what they've been doing, but also it's very important that they will not respond to false signals. And that's the second point. We see that spoofing is becoming a larger threat to agriculture nowadays, especially on the eastern side of the European Union. We get reports from farmers in Finland and the Baltics and even Romania that their GNSS is disturbed through spoofing and they cannot operate in an efficient way. So therefore we are very, this hashtag project is introducing ways of using OSNMA to make the data sets authenticated. So when they are used in a downstream process, everybody can check, yes, this was the original and the genuine track, and this has not been tampered by either intentional or non-intentional by any other source. May I have the second slide, please? So we built a little a demonstrator. This is showing the Earth observation element, but we do similar things for the GNSS. Basically, what we do is we identify whether the source is untampered, and then you see on the bottom left, you see that there's a validated by hashtag, this green sign. Now on the right image, you see that we fiddled in a hashtag symbol in the same image. It's nowadays also very easy to manipulate satellite data, Earth observation data. So we filled it in, and but then of course we couldn't identify that this was a genuine image. So you see the red mark, hashtag validation failed. So that's the way we envision it will operate in future, that we can identify truthful and wrongful data sets, and that's very important in agriculture. As I said, for the autonomous machinery and for the reporting of all kinds of data. That was it. Thank you.
Thank you, Tama. Are there any questions for now, or can we go to Martin? I think so. Thank you. Martin, the floor is yours.
Yeah, good afternoon, and thank you for the invitation to talk about the new Dutch navigation policy. I hope my slides are, everybody can see them? Maybe
Yes.
you can confirm. All right, good. I take over my colleague, Kees, who could unfortunately not be here. I'm working for 2.5 years now at the Ministry of Infrastructure and Water Management in the team Space. And we are located next to the Hague Central Station in the big square glass building. And yeah, we, together with some other ministries, we are joint responsible for the space policy in the Netherlands under the coordination and supervision of economic affairs. But we are policy responsible for the PNT policy, so position, navigation, and timing. And we scratched already the satellite-based. So that's also what I want to make clear with this presentation. It's broader than only GNSS. Yeah, I'm responsible for setting up the competent PRS authority. Already Bas told you about the Galileo PRS, and we are making it available to users within the Netherlands. They have to be authorized by us, but it's not only government, but also vital sectors and others can make use of PRS. We also helped in setting up the Galileo sensor station in Bonaire, and previously we did also that with the Galileo reference control center in Noordwijk. We try to create awareness about resilience and the vulnerabilities of GNSS and dependencies for critical infrastructures. It's called the ECUS program in Dutch, and we promote the integration of Earth observation data in policy development, especially within our own ministry. GNSS is used everywhere, all kinds of applications, but what we see is that often the dependency on GNSS underneath all these processes and systems is unknown, and also the vulnerability is unknown. But as you can imagine, GNSS is responsible for very high economic value for the EU. It's estimated at 260 billion euros in a year, and it's fastly growing as well. We think that has something to do with further automation and with use of it in logistics services. But it's not only the navigation, it's also especially timing, which is used in energy networks, finance sector, and the telecom sector. And if 1 week this GNSS is not available at all, it would cause a huge damage to the society. And the UK has calculated that 1 week of loss would cause 9 billion euros of damage to society in 1 week. Like was said before, we see an increasing threat of jamming and spoofing. It's not only in crisis areas like in the Middle East, but also across the Russian border and also in the Baltic Sea. It's ever increasing, especially also the use of spoofing, which is especially dangerous because it's not always, you can detect jamming, but you do not always detect spoofing. And then, it can lead to falsified PNT can lead to various errors. Of course, to this emerging threat, there's a lot of reactions. The EU already has a lot of response to this in strategic autonomy, in European competitiveness, also in the space law and in the regulation area. And there's also a lot of investigations how to protect against this jamming and spoofing. Especially the UK has done a lot of good research on this, but also USPA and ESA, and they also come up with a kind of this overview you see in this scheme on how to tackle this jamming and spoofing threat. So we in the Netherlands have to do also something. And we want to, our goal is to protect users in the Netherlands. Every Netherlands user should have access to reliable PNT, even in the event of jamming and spoofing. And we focused a lot on awareness, but now we want to also that we come into action. So we need to protect our systems. They should become redundant to get resilience PNT. And we see 4 pillars in this. So one of them, which we already did a lot on, is improved GNSS. We focus on GNSS. But in fact, GNSS might not be good enough. Also with the improvements, we need also to have complementary PNT interference monitoring, and we need to take actions as a government, and also the users should take actions. So this new PNT policy is under construction. We talk a lot with users of PNT, and we organized PNT input sessions. And we want to propose that within our own ministry to also get attention, but also get investments in this. So improved GNSS, you are familiar with this, and already this was told by Marcus. The Galileo system offers many services, and this is not going well, but good that Marcus already has told you this overview. In this is also the PRS, and I will tell you a little bit more about that, in addition to what Bas already told you about it. So PRS protects is the GNSS service that best protects you against jamming and spoofing because of its nature, with using multiple frequency bands, all kinds of modulation techniques, also to detect spoofing, to detect meakening. And meakening is a special form of spoofing and replay of real satellite signals. In the later stage, so then you also have a falsified location or time. And what we see in practice is that in situations in real that OS can be spoofed or jammed, and PRS is still working. But of course, it's not 100%. So if you do brute force jamming, you also will cause PRS to not functioning anymore. Well, the military is especially interested in using PRS, so they will be our biggest user in the near future. They will use it in helicopters, and there's also a lot done lately in the Geo project on receivers. So PRS receivers are much smaller now. They can also be put on drones, for instance, and they are also getting cheaper. We have a catalog of PRS items nowadays, and PRS as a service is hopefully later this year, it will become initially operational. And Spain uses this for the Navy as well. In civil side, it's more challenging, I would say, because you also need to comply to all kinds of security rules. Defense knows how to do it, but police, ambulances, and fire brigades might not have that special treatment already for ComSec items in place. But there was a successful test done in Berlin with fire brigades, with ambulances, emergency services, and this proved that also PRS can be of big help in the civil environment. So, of course, there's a lot of innovation going on in GNSS. Also with relation to PRS, so high accuracy service, and also the search and rescue will become available under the hood of PRS, so in an encrypted version as well. And this work on Galileo second generation, where we will have a better accuracy, much more flexibility by reconfigurable digitally payloads, and also inter-satellite links, optical, which makes it also more, less vulnerable, I would say. We also participate in the mission critical review of LEO PNT, where we say, okay, these functionalities LEO PNT should have. LEO PNT is low Earth orbit. You can compare it to the Starlink, but this is focused on position, navigation, and timing. It started as an ESA initiative. I think they launched 2 satellites called Celeste in the Celeste program. And this is the start, and ESA hopes that we will, as a European Commission, invest in this LEO PNT system, and we already think about what functionalities it should have. The advantages are that because it's closer to Earth, it has a stronger signal, so it's harder to jam. It has better coverage in, for instance, cities, and it's also going to be in a version with PRS. And we think that it's going to be the same as the PRS service, and same system, same technique. And then we can also use the systems we have as a CPA in supporting the PRS on LEO PNT. But the conclusion on improved GNSS is, we all have innovations to enhance the GNSS, but it does not fully resolve its vulnerabilities. And that's the new thing in this PNT policy, what we have. So we need to have complementary PNT in addition to GNSS. So resilient PNT requires multiple independent sources for both location and time. And you can think of, there are a lot of complementary PNT techniques like ELORAN, R-mode, fiber distribution network, inertial systems, and signal intelligence. And we also have the mobile network in a few versions, which can give you position and time information. And there are also new techniques like Earth geomagnetic navigation, for instance, all very promising, but they are still not all there yet. And they also have a limited coverage, or they have a limited accuracy. So in practice, in more than 90% of all cases for PNT, GNSS is used, whether or not with an encrypted version. So yeah, we think as a fallback when you really have jamming and spoofing also in Western Europe, you need to look at backup, and these are all kinds of possibilities we need to have a further look into. And for an application, it can be different what you want to choose as a fallback or as a complementary PNT. It depends on the application itself, the accuracy you need, and the costs involved. We look especially into ELORAN. Also, the UK invests a lot in ELORAN. It's a new version, enhanced LoRaN. It's of LoRaN C. They still have stations working stations in the UK. The signal from Enforn you can also receive in the Netherlands, but you need more stations, multiple stations, to get also a position. The UK is working on that, and also France is looking into it, and Germany. We are not sure if a station in the Netherlands would actually help. But because they're already, if France and Germany and the UK already has it, then an extra station in the Netherlands does not really contribute. But still, we need to look into this initiative and see whether it could help. For instance, for maritime applications. It's remarkably good for timing and timing distribution, and it has not that high accuracy, but as GNSS, so that's also the same for R-mode. R-mode is something that's also in the maritime sector used, although it's now especially of interest in the Baltic Sea. And but it's also a technique that requires other receivers, and also it has it cannot be used for timing, for instance. So all those techniques have their own characteristics, you would say. Then there is GNSS interference monitoring. You cannot manage what you cannot measure, I would say. So do you want to know also how we have to deal with GNSS interference? This requires the coordination of multiple parties. We have in Holland the RDI's, it's the Digital Infrastructure Agency, which is now responsible for measuring interference, but they do it at a very broad level in a broad frequency range. And we think it should be more focused also on GNSS interference. But there are a lot of questions still to be answered. So what is the scope of our level of detail? Do we want to have it for military purposes, civil or dual? And in what way do we want to cooperate with Europe? Because you see a screenshot of the EcuRON system, which is really also with crowdsourced techniques. And we will try to have a look at some probes, but do we want to share, is it a policy to share GNSS interference data with other countries? Because it's also a little bit of intelligence data. A lot of questions to be answered. And then a fourth pillar under our new PNT policy is the government's and user actions. So as a government, we want to have a clear position and clear direction in which we want to go. So we still have some questions to answer, but we indeed want to search and find our way with a better interaction with users, what users want, all related to this reliable PNT that we want to offer in the Netherlands. We want to give them better access to information, not do ad hoc initiative, but a clear direction, working together in an incorporated way, and also across borders. Within our own ministry, we do have to do a coordination of the investments within the PNT domain, and the exact form is still to be determined. But we are definitely taking on an advisory role and to do the coordination. If you look at governmental action, we already, as a government, provide infrastructure. We encourage and stimulate innovation. It helps us forward, but we also look into where the Netherlands' interests lie. Where can the Netherlands and Netherlands firms really add value? And sometimes it's better to buy the common off the shelf. Our policy is not meaning that we have already done some tough investment decisions. We think we should do this focused exploration first. And it's now too early to decide whether we want to invest millions in a national PRS receiver, or in our own e-LoRaWAN towers, or in R-mode, or in a fiber optic time network. The cost and feasibility are not yet entirely clear. This fiber timing network, that's really very also a clear goal, that we want to distribute the time via fiber to all the critical infrastructures in the Netherlands. And it is also where you see other countries invest in, and that's definitely also a very specific goal, what we want to do research on as well. But we need other parties for the implementation, and also their position is not yet clear, and our available budget is not yet clear. So these are some disclaimers on our PNT policy. But we are definitely taking a few good steps in the right direction with this. What can users do themselves? Well, at least they should know for their application, do an analysis on the PNT resilience and the risk they have when knowing that GNSS can be vulnerable. We have provided a resilience assessment tool on the pntportal.eu. I advise you to go there and also use that tool. You can think of many measures to strengthen PNT systems, the diversification of sources, the complementary PNT, what I'm talking about. You can also detect and mitigate disruptions using specific antennas and fallback procedures and process, and also train your operators in case of what to do in case of jamming and spoofing. So if you look at, for instance, receiver level, you can use encryption, you can use detection and direction of the direction of the signal arrival. You can detect signal distortion. You can use a GNSS, a non-GNSS backup. You can protect yourself against cyber attacks and do some antenna protection. For instance, you can use active antennas or a choke ring to have less problems with jamming and spoofing. And also looking at your receiver, you can apply a kind of zero trust architecture to detect attacks and lessen their impact and mitigate the risk that you still have in the center a reliable PNT. A lot can be done also in that respect. And maybe this, looking at from a technology point of view, a system approach where we use both complementary PNT like ELORAN or the time distribution network, together with better GNSS, together with resilience and GNSS interference monitoring, and let that work together to take the right actions at the right time. So that's also called the system of system approach. And that's, I think, the way we want to go into that direction. But we have to do that in a few steps, and it will take some time. So now I come to the conclusion. So GNSS, especially Galileo, is a very accurate, available, and autonomous, but it's also vulnerable. And our ministry is coming with this new navigation policy to get awareness, and in these 4 pillars that I explained. So improved GNSS, complementary PNT, interference monitoring, and take the right actions as a government and also the users to get resilient PNT.
Thank you, Martin.
I will now share I'll stop the sharing.
I see 2 questions in the chat. I'm not certain if it's the best question for you or maybe for the next 2 presenters. Yuri is asking, will HAS work with zero trust antennas?
I think that's better for the next presentation.
I think so. And then the question
HAS,
for Fini is also related to the HAS service. So we will keep the questions for Teresa and Emilio. Martin, thank you so much for sharing this new policy from the Ministry of ENV. And now, given the time, I will hand over the presentation to Teresa and her colleague. So thank you.
Thank you.
Thank you very much and good afternoon. I am Teresa Martinez from EUSPA GNSS Service Center. I'm going to share my screen. Okay, can you confirm that you can see the screen? Okay, perfect. So thank you very much for joining. I think a huge audience today, so we are very happy. Building on this previous webinar that was more basic, this session will provide a deeper insight into 2 of Galileo's key value added service, the high accuracy service and HAS, and the open service navigation message authentication, OSNMA. The webinar will cover the fundamentals of both services, followed by more in-depth and practical content that will be explained by my colleague Emilio. And it will also include the capabilities, benefit, and setups of receivers. So I think Emilio will answer this technical question in the second part of the presentation. So. Okay, so today we have this agenda that I already explained. So let's go, please, just to make this session a bit interactive. I appreciate if you can scan this QR code that I will also share to be the answer online. Please. We have 2 questions just to know your needs.
You can also type slido.com and inject that code.
Can you scan the QR code? Anas, I see that yeah, it's possible to scan the QR. Okay.
It works.
It works. Okay, perfect. We can see the results in on live. So what is the biggest challenge in your current related activities? Because this is also important to understand what are your needs or for the development of the current service and for the roadmap of Galileo. So thank you for answering. I see, yeah, due to the Geo-information community, maybe the position accuracy is one of the most relevant needs. Okay, you can answer but I would like to continue to the next one. Almost half of the participant needs require position accuracy. The next question, if you are using HAS and OpenSNMA, it's true that we haven't explained yet OpenSNMA, but for sure that you know if you are using them in your activities or not before explaining. Okay, you are aware of them, but not using them, most of you. Okay, you can continue. Okay, thank you very much. Very important for us, as I mentioned in the first webinar, to know what are your needs, your requirements. We are working on this very close to the users, so that's really important for us. So let me go to the next. Okay, we will start with the fundamental of high accuracy service. We provided some overview in the previous webinar, but now I will explain a bit more the fundamentals, and then my colleague Emilio will give you more information, more technical information. So, as I mentioned in the webinar one, standalone GNSS accuracy sometimes is not enough for some application, and some techniques, or let's say capabilities, are multi-frequency receivers to mitigate ionospheric errors, the carrier phase measurements, and differential GNSS. As discussed in the previous webinar, some techniques have been developed to enhance GNSS position accuracy beyond the level provided by standalone satellite signals. This includes RTK, real-time cinematic, PPP, precise point position, PPP RTK, each offering different characteristics and trade-offs in terms of accuracy, coverage, infrastructure, requirements, and convergence time. I'm not going to explain because we saw this in the previous webinar. Just to remind you, HAS is a Galileo High Accuracy Service, is based on PPP corrections, builds on these concepts by providing a precise orbit, clock, and bias correction to users worldwide. One of the key advantages of HAS is that it's free, global, and operational 24/7, unlike many high accuracy solutions that depend on regional networks or commercial subscription. So a correction are broadcast through Galileo E6B signal, we will see now in the next slide, and also via internet, enable a broad accessibility and facilitating integration in a wide range of receiver and application. So this is just a reminder. Here you can see a bit the context of why HAS. HAS is here in this picture because it's following the Eurospace regulation, the user needs. If you see here in this picture the accuracy of different techniques, I think somehow this service bridges the gap between standard GNSS accuracy, sub-meter and centimeter level positioning service, and again is free, open, and globally available. So no internet connection is required. So here is where we can locate, let's say, Galileo HAS together with another GNSS techniques and some of the advantages. Galileo HAS provides user with precise correction, as I mentioned, that compensates some GNSS errors. HAS this service is distributed through two complementary channels. The first one is signal in space, the Galileo E6B signal, allowing HAS-enabled receiver to obtain correction directly from the satellites without the need on external communication networks. And the other channel is terrestrial dissemination via the internet, enable user and application to access the same correction data through online services and integrate them into processing solutions. So this dual distribution approach provides user with a flexible, global, and robust way to access high accuracy correction anytime, anywhere. Here you have two documents if you are interested in more information about these two channels. This is something that I already commented in the previous webinar, but very quick, I would like to explain a bit that again, Galileo has provided correction that can be applied not only to Galileo, but also GPS. So it's applied to both Galileo and GPS signals, enable multi-constellation high accuracy positioning. So by supporting Galileo and GPS has improved positioning availability, robustness, and performance. HAS is designed for multi-frequency receiver, allowing user to reduce ionospheric errors and achieve faster convergent time to high accuracy positioning. This is also important for some application. And here we have the service levels and roadmap. In the roadmap, we have the phase 0, phase 1, where we are here, phase 2, and has evolution based on the user requirements. We are now in phase 1. And also we have here the different service levels and the different characteristics. Galileo has evolved through different service level. The service level 1 provides precise orbit clock and bias correction, while the service level 2 will add atmospheric correction to further improve performance. And as you can see here, it will reduce the convergent times. So this progressive roadmap enhances the capabilities of the service while maintaining a global free and the availability. Okay, here you can see some performance that we explain with my colleagues. Will give you more information about performance, but here I invite you to visit the web page because the characteristics, performance figures, and service commitments of the initial service are described in SDD document, the Galileo HAS service definition document. And you will see here in the table the typical HAS position accuracy in horizontal and vertical with using Galileo only on Galileo and GPS. You will see examples or text where you will see that even better performance are met. To benefit from Galileo HAS, user need first a HAS-compatible Galileo receiver capable of receiving, decoding, and applying the correction, either, as I mentioned, through signal in space or via internet. And second, a precise point positioning which use the HAS correction to compute a high accuracy position. Together, these components enable users to achieve improved positioning accuracy compared with standard GNSS navigation. Okay, next slide. Here you can see I would like to mention the HAS UA is a reference implementation algorithm used to assess the performance. It provides a valuable benchmark and implementation guidance for developing a compatible PPP solution. So we invite you to explore more about this algorithm. The HAS UA is a precise point positioning algorithm based on external Kalman filter with estimate the user position while incorporating the HAS correction data. The current implementation uses a float ambiguity solution, providing positioning accuracy at the decimeter level. This performance with this algorithm has been evaluated under kinematic condition, meaning that the user is assumed to be moving. And to achieve the position available targets defined for the service, a concrete number of satellites must be visible. If you use Galileo, at least 5 satellites, and Galileo and GPS at least 8 satellites. This demonstrates the benefit of combining both Galileo and GPS measurements, which increase satellite availability and improves the continuity of high accuracy positioning. On the right part is an illustration is a HAS comparison done in 2023 using both Galileo and GPS, and you can see that HAS significantly reduce position error compared to standard GNSS processing. Here, very briefly, the Galileo HAS architecture. HAS is supported by a dedicated ground and space infrastructure that generates, validates, distributes, and monitors the high accuracy correction data provided to user. At the core of the system is the HAS data generator, which processes the observation collected from a network or Galileo sensor station and compute the precise orbit, clock, and bias correction. These corrections are validated and managed through the Galileo ground segment, including the ground control center, which oversees system operation and maintenance. The correction data is then transmitted to the space segment through the uplink station, allowing it to be broadcast worldwide via the Galileo satellites. In parallel, the corrections are also distributed through internet-based service. And the GSC, the GNSS Service Centers, as commented many times, serves as the main user interface for Galileo HAS, providing access to service information, documentation, data dissemination, and user support. So, yeah, this is more or less the HAS architecture for the high accuracy service. And and here you can see the Galileo HAS service area. The maps shows the current Galileo HAS service area. You can see the regions that are currently excluded from the service area. The blue shaded rectangles over part of the Pacific Ocean and East Asia and Oceania. The service has been designed to provide global coverage, but the initial service does not yet guarantee the same level of performance worldwide. This is important. So within the defined service area, Galileo HAS commits to meeting the minimum performance levels specified in the document that I mentioned before, including targets for accuracy, availability, and continuity. I have to mention that users located in the excluded areas can still receive and use Galileo HAS correction, and the service may provide good position and performance, but these regions, Galileo does not, let's say, formally commit, guarantee that the published minimum performance level will be achieved. Let's say that the service remains available, but the performance is worse, okay? This is the Galileo HAS service area worldwide. Here you have many documentation. Some of them are very recent because HAS was launched in 2023. This document refers to technical interfaces and data specification. I invite you to explore the web page. You have here the link. The system service description explains how Galileo service system works at a high level, including function and usage. You have also for developers specific documents based on the algorithm, and you have here the link. So in short, SD is like the overview. As I see this, the system data and exchange rules. You have here all the documentation that can be useful if you want to go into detail. Here we go to the Galileo has target markets. There are many words, sorry for this slide. More or less the advantages are always the same. High accuracy, centimeter level, no local infrastructure needed, free service, wide industry coverage worldwide, and it improved the autonomy and the safety. So in particular for surveying and geomatics, has removed subscription costs. Okay, you have to analyze when you need to use this service or not. Provide decimeter level accuracy. Okay, it's not compatible with other solution, RTK and PPP, but you don't need a base station. So make it is suitable for some topographic or geo-information work, geographic information system. In areas where you need requires no data link. So this is very useful if you need to work in difficult or remote areas or offshore environments. So let's say that this application could be useful for this mapping, cadastral, hydrographic survey, and offshore explanation. Also, of course, is useful for other market segments like agriculture, aviation and drones, maritime, railroad, automotive, infrastructure, and utilities. And here you will see and you can explore in detail. Okay, here we have some EUSPA projects. In the webinar, in the first webinar, we explained some success stories that we have in the GSC website, but here we have some HAS, even some of them are HAS and OSNMA project that you can explore in the EUSPA webpage. Most of them or all of them are fundamental elements. It's a program, European Research and Development Funding, a program that supports company and research groups to develop GNSS chipset, receiver and antennas. Here you can see the islet, the Phonex project, Dream, newspaper, and Union. The islet developed a close to market maritime GNSS receiver integrating HAS and OSNMA to provide accuracy. Phonex develops a low-cost triple frequency Galileo HAS for precision agriculture, exploiting PPP. The third project, Dreams, has an OSNMA projects focused on advanced multi-sensor positioning by combining Galileo HAS with complementary sensors. Newspaper aimed to enhance precise positioning with innovative GNSS receiver, and the Union and differential and combined position engine is also a finished project that we invite you to explore in the web page. Just to finish, the fundamentals of HAS. Here is a practical use case that we have recently published in EUSPA webpage, where you can see the errors. EUSPA tested this HAS in a real farming environment to check if it's good enough for precision agriculture. The test was done in Spain as a joint collaboration between EUSPA, Case New Holland, and Hemisphere GNSS. This kind of test we are currently doing, and we invite you, if you are interested, to contact us. This graph shows how the position error of Galileo high accuracy evolves over time during a real test. At the beginning, during the convergence phase, both horizontal and vertical errors are relatively high and stable, reaching several decimeters. As time progressed, the errors decrease rapidly and the system converges, meaning it reaches a stable and reliable solution. And after this point, in the longer evaluation period, both errors, horizontal and vertical, remain very low and stable, mostly within a few centimeters. This part of the graph is what is used to assess the absolute accuracy and pass-to-pass accuracy. You have here the link, and you can see the accuracy that was achieved much better than the commitment, let's say, for both for horizontal and also vertical. So we have success story, projects, and tests that you can explore. And this is all from my side. My colleague Emilio will continue has in-depth and practical content. He will also answer about the receiver question. Thank you.
Okay, thank you very much. I wonder if you see my presentation. My name is Emilio Gonzalez. I'm a colleague of Teresa at the GSC, and I want to complement a bit this complete presentation by her, just on technical topics. First, a review on the high-level architecture of the Galileo HAS infrastructure. We have, as Teresa showed, the high accuracy data generator, the HADG, that is located at the GSC, and the navigation message that is on the E6B band is sent to the Galileo core infrastructure, to the Galileo control centers, and then this is relayed to the uplink stations, and this is sent to the satellites. The satellites relay this information to the users and through the signal in space, and this is acquired by the users with the receivers. Alternatively, the high accuracy data is sent through the internet from the GSC, and it is sent to the user through conventional internet means. The signal is also getting to the Galileo sensor stations for closing the loop and evaluating the corrections at the HADG. What is this message consisting of? We have a lot of blocks of information. We have 25 seconds, I mean 50 seconds. There's a message per second with slow and fast messages, and the slow messages consist of orbit and code biases, and the clock information is in the fast message, and there are some other dummy messages that will be filled in the future. The signal is encoded through the Reed-Solomon algorithm. That this is usually used in satellite communication. Is to prevent fading loss, and it's useful to recover the message if you have only a number of these pages to prevent, as I said, losses of blocks of information on one signal. And once you get these corrections, these have to be processed by the user receiver through user algorithm. And currently, there's a showed that there is a hash reference user algorithm published. This user algorithm is the one that has been used to validate the service. It is not the only implementation possible, but this is the reference. And its main features you have there, it is a PPP algorithm that is based on an extended Kalman filter, which currently is based on a float ambiguity resolution with uncombined single difference processing. And besides, there are outlier detection with receiver autonomous integrity monitoring, with cycle slip detection and corrections. There are assumption of kinematic conditions. Of course, if you set the filter to have in static conditions, and the user is static, of course, the performance improves significantly. But with these kinematic conditions, we get the performance that we are seeing along the presentation. And there's a news that there's also showed this algorithm, the implementation of this algorithm is available to anyone that wants to have it on your computer, on any element that you want to use. And here I can answer one of the questions, if it is possible to use HAS on a smartphone. And the answer is depend. It depends. If you are using a conventional terminal, the antenna is not E6 capable, E6B capable. So you will not be able to use the corrections right through the channel that comes from the satellite to get the corrections. So you would need to get the information through the internet data dissemination channels, through the IDD, through the internet. So this is one aspect. Another aspect is that the reference algorithm is suitable for dual frequencies. So not any smartphone will be capable. So you need to get a double frequency algorithm terminal E1, E5 to be able to get the most from this algorithm. And of course, this algorithm must be coded into an app. And for instance, you get this software or the specification that it's in the algorithm technical note. You can code it, and of course, you need to apply that to pseudo ranges that are coming from the terminal. So you need to use libraries that allows this, and this is not present in all the terminals. There are Android terminals that release libraries that provide the pseudo range, the measurements, on top of which you could add these corrections and provide a Galileo HAS solution. Last but not least, the antenna in a smartphone is not optimized to these kind of high accuracy solutions. So maybe even if you followed all these steps, the performance that you achieve is not all the best that you could expect. But in short, the possibility is this is possible. Yes, it's possible. On the second question, I don't know about the details of this zero trust system, but if it is an E6 antenna, even if it is a CRPA antenna, if it is E6 capable, then yes, why not? You could use it. So I don't know if this specific solution is a vendor solution that is E1 only or double frequency, or it's just the can be used to any user receiver. If it is the latter, then as long as it is E6B antenna, you could use the signal in the space. Besides, if you only have a dual frequency antenna, the corrections can be retrieved still through the IDD channel, through the internet. Okay, so there are a list of HAS commercial receivers on the GSE website. Here you have a glimpse of that list, and there's an increasing number of manufacturers that are providing Galileo HAS. You can see some names there, and we are following the implementation of HAS in the market. So the list is always increasing. Perhaps it's not complete. If you have notice of any other unit, please let us know, and we will correct the list. So here you got for your reference on the usual segment or applications where each model can be used. We also deliver quarterly performance reports that are tailored at system levels. Here you've got some performance. Later on, there will be a presentation where performance will be assessed more thoroughly. And to use the corrections, we will give some brief guidelines. This will not be a hands-on experience, but you will have some clues. First, you need a receiver, of course. You need a receiver with, assuming that you got the information from the satellite, with a E6 antenna, and you need a laptop to configure the receiver. So the configuration is a one-off activity. You connect the receiver through a USB port, for instance, and you need a vendor application, like in this case, the Unicore UM980 UPRECISE application. And you need to send commands for both configuring PPP into this receiver, and also to configure the logs, the outputs, so that you can use later on to the solutions, or if you need more information to get measurements or whatever you need for your application. Here you got a link of the commands manual for this specific receiver, but the way of using Galileo HAS is more or less the same in other products. In this example, here's a glimpse of this application. You precisely where you got a space where you can see the constellation, a place where you entry the commands and send them to the receiver for configuration, and where you also get the logs coming from the receiver. And then there's another area where the tracking status, the number of satellites, and so on, where you can display that. There are, of course, some controls for the selection of the serial ports and the connect-disconnect button, of course. And this is the kind of commands that you enter in this case. The first set of commands is for the configuration of the receiver. You configure, for instance, the algorithm PPP enable, config PPP enable E6 HAS. You are telling the receiver to get the information for the PPP algorithm from E6. Then you need to configure the datum of the solution, in this case WGS84, and then limits for the threshold for the convergence metrics, and the mode as a base receiver. You mask Baidu and GLONASS because you only need GPS and Galileo. And then the second block is for configuring the logs. In this case, the systems, time, or the GSB, the satellites, GGA, measurements, and so on. And also this one for raw data for later rings conversion if you need it. This is just an example. So this is all that I wanted to highlight about HAS on the practical side. And this summary slide it tells some key takeaways. As you know, this Galileo service is delivering high precision corrections that include satellite orbit, clock, and bias information. Right now, the phase 1 initial service has coarse bias information. In the next year, probably the phase 2 will provide phase bias as well. There will be ionosphere corrections in the ECAC area, in the Europe area, and there will be a performance improvement in general in accuracy, but significantly regarding convergence. Of course, with this ionosphere correction, the convergence time will decrease, but overall, as the number of sensor stations will also increase, we may expect a better convergence time, because there will be also ambiguity resolution in the user algorithm. There will be also authentication in the solution. There will be other corrections like satellite corrections accuracy. There will be an improvement in overall. All in all, the system as it is today is delivering decimeter level accuracy, and there will be more precision with high-end receivers. And there are two channels, one through the signaling space, E6B band, and another through terrestrial distribution over the internet, which is called the IDD. If you want to get the correction through the internet, just register through the GSC website. There's a form there where you can ask for these kind of solutions, and then the information will arrive to your receiver through RTCM streams that you can apply, as you can use with other RTK or PPP services. Galileo HAS uses both Galileo and GPS, dual frequency or triple frequency solutions, and you can get better in position and performance, also time and performance. And finally, it is designed for a wide range of professional applications. So thank you very much. I will continue later on with OSNMA.
Okay, hello again. I guess that you can see my screen. So one moment. Okay, I will explain OSNMA, the fundamentals, and then Emilio will continue with the session. So before we describe OSNMA, it's important to understand why GNSS resilience has become such a critical topic. Here you can see in this graphic in the right part, in Baltic Sea, thousands of occurrences are detected every month. So this is something also relevant, also was mentioned by Martin and other speakers. The problem is that the GNSS signals are open, low power, and globally available. So it makes them it's important for Geo-information and other application, but they are vulnerable to interference and manipulation. One major threat is jamming, where a malicious transmitter emits radio signals that overwhelm GNSS frequency, causing loss of positioning and timing service. And another is spoofing, where fake GNSS-like signals are broadcast with falsified navigation data. tricking receiver into computing incorrect position or time without immediate detection. So a traditional open service receiver cannot verify the origin or integrity of the navigation message, which makes GNSS again vulnerable to disruption and deception. And this creates the need for authentication mechanisms to increase trust in position and timing data. So to address this is the context. Galileo introduced open service navigation message authentication, which adds cryptographic authentication. It is based on cryptographic function, allowing receiver to verify that the data is authentic and has not been modified. So this is the context of OSNMA. It's a free capability as well as has service within GNSS. Provides cryptographic authentication I mentioned before, and the main goal is to allow receiver to verify that the information they use for positioning truly comes from a trusted Galileo source and has not been modified. This is not a technique to really prevent the spoofing. We will see along what is the real meaning, but it's like a first step and it could really help for some application. OSNMA is fully compatible with the system receiver because the authentication data is embedded within the E1B INAV message, meaning it's not required changes to the core signal structure or degrade performance. The OSNMA is divided into main parts, the HK root in the first 8 bits and the MAC, the next 32 bits, let's say, for the message authentication codes, let's say, it has like a place for this authentication message. That's why OSNMA does not affect the performance of the open service or legacy receivers, ensuring backward compatibility. Overall, it authenticates key navigation components such as ephemerides, satellite clocks, and timing data, improving the robustness and resilience of Galileo-based positioning against spoofing and data manipulation. Here you can see an scheme that will be explained in more detail by Emilio. Let's say that the information broadcast by Galileo satellites include the open service, which is authenticated by OSNMA together with the elements that are the digital signature, the Tesla key, and the message authentication code, MAC. MAC. These are common elements of the protocol and required for processing the authentication codes and authentication types. There are three types, three different authentication types that are broadcast to the receiver. You can see here in different colors. This is an example, the receiver, a drone. Also retrieve required crypto material from IDD. We will see on GSC here this material you can access by this mean that we'll explain later. And by processing this information and executing the corresponding crypto function, the receiver can verify if the navigation received from signaling space is authenticated or not. In case it's not, it's better not use. This is a general scheme, but we will be explaining in more detail. Just to mention, I don't want to go into detail. This is some prerequisites for using Galileo OSNMA. First is the code OSNMA message. The receiver can read special OSNMA fields in the Galileo signals. Use cryptographic. It processes OSNMA data securely using the required cryptographic function. Time synchronization, it aligns with Galileo system time before processing OSNMA. Secure storage, cryptographic keys and material are stored in a safe way, safely. Trust anchors available. The receiver has access to the necessary public keys and Merkle tree root. Buffer OSNMA data. It can receive and store authentication data like tags and keys. And all of these should follow guidelines. The receiver meets Galileo SNMA rules for correct implementation and validation. There are a compliance with the Galileo SNMA receiver guidelines for the correct implementation and validation. And this is something, just to mention, some requirements for using Galileo SNMA. Again, the OSNMA documents describe different parts of Galileo authentication. You can access to this documentation through our website. Here you have the link. Here you see the different application for surveying and geomatics, automatics, time and synchronization, maritime, aviation, and critical application. Specifically for surveying and geomatics, it, let's say, protect somehow against spoof observation, because you know if the source of the signal is original or not. Supports regulatory mandates requiring verified, for example, for survey campaigns, preventing falsification or data, increase reliability. So in conclusion, let's say OSNMA strengthens satellite navigation by ensuring that signals are authentic and secure. While it does not increase accuracy, it improves reliability and resilience against spoofing attacks, making satellite navigation safer for all types of critical applications. So where it makes sense to use this service. So for when regulatory or legal compliance takes an important role, this service could be relevant for a different application. Here again, you have some projects that you can see in EUSPA webpage. In particular, the first one, the patrol, is a success story. It's very important, supported by EUSPA and European Commission. Is let's say, a consolidation of the smart tachographs regulation and the inclusion of SNMA. So it's very, very relevant, this project. Here you can see more information, the partners. Also in the right part, timing projects. You see here 3 projects. The aim is to develop a dual frequency time receiver in full compliance with requirements of the standard for timing receiver. Here you can see the ASCAR and the ISLAT. The ASCAR is a maritime project that is concluded and evolved to ISLAT project that is an ongoing project. And you can also explore is a fundamental element success story that you can explore more in the EUSPA webpage. And just to finish, Galileo Authentication Service, OSNMA is operational just now. Will be explaining more detail the technical characteristic and receiver by Emilio. Authenticate navigation message. On the contrary, the upcoming service, the signal authentication service, authenticates the range level. So the tests are actually being in place, coordinated by EUSPA and European Commission. The initial service declaration foreseen in 2027. So OSNMA, let's say, will be complemented by this service, will offer range authentication. So we are evolving, offering more robust and services. So here, again, just to finish my part, because I don't want to interrupt Emilio, we don't have much time. I really appreciate that you can scan this QR code. And I will, again, share in here. Okay, here, are you satisfied with use of HASH and OSNMA is the first question. In case you use these services, if you don't use, you also have this option to answer the question. Also, you can answer has as well, so you can answer more than one. You can choose more than one option. So let's say it's two questions in one. You can please answer the OSNMA part and also the has part. Okay, thank you. Okay, so many of you cannot evaluate because you are not using. Okay, I will go to the next one. It's about OSNMA. This is feel free to write down what you want. How do you see Galileo OSNMA benefiting your application or operation? So, for example, you need more reliable data in your survey campaigns, support for regulation. If it's useful, maybe it's not useful, and you can also answer that maybe it's not appropriate for your current activities. Okay, improve resilience against spoofing aviation, spoofing resilience. Okay, and the next question and the last one. What will encourage you to adopt Galileo SNMA in your products or services? So what can we do for you in order to make OSNMA more attractive? You need more technical support, more, I don't know, opportunities, tests, whatever you need, please let us know. It's important for us to know how we can support you in the adoption of Galileo SNMA. More general information about receiver, and also maybe could give information for Emilio to focus in maybe particular parts of the second of the advanced section. More information about the receiver. Okay, in principle you have all the OSNMA enables a receiver, but also could be complemented by Emilio if you have any question or any specific. Getting in touch with market partners that can help a lot. Also, yeah, EUSPA can support on this. We can also analyze this answer. So you can answer, but I'm stopping sharing my screen, and yeah, you can continue answering. And Emilio, the floor is yours for the second part.
Okay, thank you, Teresa. Thanks for the information to the audience. Some of the topics that are requested, we can already provide from the GSC. So we have got a help desk where you can put your queries, and we will be glad to answer. Okay, in the next slides, I will provide some slide introduction to how OSNMA works. I will not provide much detail. Well, some ideas have been already presented. First one, Galileo OSNMA has got these three features. One, as Teresa said, the use of cryptographic functions. The key characteristic is that the direct problem is easy, but the inverse is very, very complicated. Perhaps you need years to compute and to get the right solution. These cryptographic functions are used currently in many of your daily applications with the banks, the digital signature. These are cryptographic functions, okay? And here they are using keys that follow what is called the Tesla protocol. We will see later on. Another feature is the cross-authentication. The OSNMA allows authentication of data from one satellite to other satellites. Not only authentication from the same satellites that broadcast the information. And third feature is the layered validation of the data. And we will see later on. This occurs several times. And how is the OSNMA functioning? Well, at the GSC, we got the generating element of the keys where we apply with the navigation message that is to be broadcast and get the tag, the solution of this cryptographic function. So both the keys and the tags are sent into the signal, and this is broadcast to the users. And once you get message key and the potential result, you apply in the receiver with the same algorithm and compare. And this is if the comparison is okay, then the message is authenticated, and if not, there's potentially spoofing attack. This is the basic functioning, but now we enter in this layered mechanism of security. So first, should the receiver rely on this key? How to check that this is not also spoofed data? Then we've got this Tesla functioning. Well, the Tesla protocol works by the transmission of the key that is generated through successive hashes, successive application of this function until we get a key, a root key, no, the K0. This set of consecutive hashes is called the Tesla chain. It starts with a random key seed, Kn, that is secret and only is known by the OSNMA provider, and you get all these consecutive hashes until we get this K root. The trick is that the Tesla keys are broadcast in opposite sequence to their generation. So a spoofer cannot fake a given key from the past, because you cannot get the inverse function. And this is a smart way of trying to avoid meaconing. Here in this diagram, we will see again the functioning and how a receiver will get the pieces of information and get the check on the authentication of the message. The information in the signal in the space is the navigation message, the Tesla chain key, the tag, the result that we are going to compare with, and the root key. First, the Tesla root key is authenticated by means of the public key. This public key is authenticated by another piece of data that will be available at the receiver, and we will see later on. If this Tesla root key is authenticated, then we get through successive hashes the Tesla key that is applicable to that instant. Then we get the navigation message, apply this digital signature algorithm, and get the result, this tag computation. And finally, if the computed tag is equal to the received tag, then the message can be assumed authentic. But another layer, shall we rely on this public key? How to check that it is not spoofed data? Then there's a further validation, which is using the Merkle tree. And the Merkle tree allows the user to verify the public key. And we have some information on this tree, some nodes, and we compute with the public key and this node information, the remaining nodes, until we get to the root tree that is included in the receiver. These are also computed through cryptographic hash functions. And here we got an example. We get, for instance, the public key 8, and we got the nodes that you can see here that are retrieved from the GSC, and then we can apply the hashes of the different information, and we are getting the upper and upper nodes until we get the top node that is checked with a root Merkle tree node that is stored in the receiver. If this computed Merkle tree node at the top is the same as the stored one, then we can say that the public key is authentic. And well, for each public key, we've got different intermediate tree nodes from the Merkle tree information that is to be input in the receiver.
Emilio,
yes?
Sorry to hop in, but we're running a bit out of time. How many minutes do you think you need for the finishing of the story?
I will finish in three or 4 minutes, I think.
Okay, perfect. Thank you.
Okay, so then you can see here the layered functioning. On one hand, the public key is checked with the top leaf stored in the receiver of the Merkle tree, and with the public key we verify the Tesla root key. The Tesla root key, we get the Tesla chain key through successive hashes, and finally with the Tesla chain key we can compute the MAC and check with the broadcast tag. And this is the summary of how the OSMA is functioning. Then, as I said, you need some information, some cryptographic material that is got from the GSC website, and there are a number of certificates that also have 3 layers: the root, subsidiary, and issuing certificate authority, and these you need to get them from the GSC. The authentication of the information was size 1 to 5, 6, 10. I will not enter into this information. Regarding the OSNMA receivers, the information in the GSC, you've got the list of OSNMA enabled receivers. And well, there are also some other information, like for instance the social media, the jammer test. I saw a question about Andoya. We ourselves haven't tested in Andoya, but we are covering some of the news there. and we are in contact with manufacturers that have tested there. Regarding the performance, I will not enter into details, just to say that we are publishing quarterly performance reports out also for authentication. You can see that the availability is very high right now. And if we want to check how do we do with an actual receiver, it's very similar as in the HAS. You need to access the receiver with an application graphical user interface, but you need to enter first this information from the GSE website and download this cryptographic material. This is an example with the Septentrio Mosaic 8 application that you can get through the browser. And there you can check that the firmware version is appropriate, because OSNMA is only available in the newest versions from 14.4 or greater. And the cryptographic information in the GSC is first you have to register and go to GSC products, in particular those OSNMA Merkle tree, which is an XML file, and the public key, that is a CRT file. And these files, depending on the specific receiver, but this needs to be input into this graphical user interface of the receiver. For instance, you edit this XML and you got the Merkle tree there, and that chunk of information, and this is the same for the public key, that information is input in the application. There you go, the OSNMA configuration Merkle tree root. In that dialog, you input the Merkle tree root and the key in the key 1 field of the OSNMA public keys. Regarding the OSNMA mode, there are two modes in Septentrio. One is the loose, that will introduce all satellites into the PBT solution, authenticated or not. And the strict will only get solutions with satellites that have been authenticated by OSNMA. And this can also be made through the receiver application. Here, in that application, you can also see the status of authentication. In this case, from this word of the Septentrio binary file. There are other pieces of software like Galmon that allows to analyze offline information. So you get the navigation message in raw format, and you can post-process it. So you can provide a lot of information. And these are some outputs of this OSNMA lib. That is another library for the analysis of OSNMA. And a summary slide. On one hand, that OSNMA is for authenticating the Galileo Open Service Navigation message. It is backward compatible, so it does not impact OS performance, and it is on L1 band, so you can use a simple receiver, and this is just an add-on software, so you can have it on a smartphone if there's an appropriate application, and you can get access to the navigation message. And important is that OSNMA authenticated the navigation message, not the position, because the spreading code, the pseudo range is not authenticated. This will come by the future signal authentication service, SAS. And well, just the last words is that we are open to your your contact. If you want to receive more information, please subscribe to the GSC, and you can get in contact through the help desk or through these emails there. We are running also user satisfaction survey, and your answers today will help us improve the services. So thank you very much. We will be glad to answer, perhaps after the following presentation.
Thank you, Emilio. There's also a question in the chat, so maybe you can have a look and answer it via typing. So then the Galileo Reference Center can take over for the next and final presentation.
Okay, thank you.
Okay, thank you, Caroline. I hope you can hear me, and I will share my screen. I hope you can also see my presentation.
Yes, all good.
Okay, thank you. So thanks everyone for staying with us all the time. We come to the final part of the presentation. We will say a few words about the Galileo Reference Center, and then focus on the HAS and OSMA performance as observed by the Galileo Reference Center. The Galileo Reference Center is based in Noordwijk in the Netherlands. Here you see the map where we are located, and a photo of our building. I will say a few words about our mission, about member state support to the Galileo Reference Center, and about the reporting, monitoring and assessment that we are doing. The DRC mission is to do independent monitoring and assessment of the service provision of Galileo, and that means all the services that we have, the services that we discussed today, but also additional services that we don't focus on today, or also future services. When feasible, we also assess the compatibility and the interoperability between Galileo and other GNSS. This means that we do a report not only on Galileo, but also the performance of GPS, on Beidou and GLONASS, and we compare these services also with Galileo. We provide service performance expertise to the program. We support investigations of service performance and service degradation. The archive function of the DRC is important. We save data over the normal operational lifetime of the system. And important is that we integrate data and products from EU member states, but also Norway, Switzerland and Iceland. And these last three countries have a special agreement with the EU to support the European GNSS programs. The support from member states are organized through what is called the Framework Partnership Agreement. What you see here is a map of Europe with all the entities that are part of it. So as you see, there are many of them, not from all EU countries yet. So we still would like to expand our cooperation further. What is important is that all these entities support independent monitoring assessment of service provision, also investigations, but in particular they have a lot of facilities in their countries that we can make use of. For example, worldwide networks of stations. They have laser ranging facilities, timing laboratories. At the DRC, we mainly monitor static performance, but in the campaigns, we make use of facilities from the member states, for example, airborne facilities, airplanes, drones, maritime, automotive, but also we do a lot of work on radio frequency interference monitoring and investigations. The DRC architecture and operational concept is that we are fully independent of the Galileo system and of the Galileo service operator, both in the technical solution and in operations. All our processes are as much as possible automatic. So we do continuous monitoring and data processing. Each of the Galileo services are monitored through what is called a key performance indicator and figures of merits. Key performance indicators are meaning that they are derived from what we call the service definition documents or from KPIs that we have agreed with the Galileo service operator. We also monitor parameters of the Galileo signals against what is called the interface control documents, and we do, as already mentioned, campaigns with member states. In the very beginning, Carmen also mentioned have facilities that we have available in USPA sites. At the Galileo Reference Center, we have a laboratory with many different receivers, COTS receivers, meaning receivers you can buy on the market. But also we have many prototypes. So OSPA is developing prototypes for receivers for new services. Often we receive these prototypes, we test them at the Galileo Reference Center. For example, the high accuracy user terminal we have at the reference center. We have dual frequency and multi-constellation receivers, which are the future receivers for aviation. We have what is called probes from AGPRON. AGPRON is a project from OSPA to monitor radio frequency interference. We do emergency warning satellite services testing. So at the moment we do some campaigns for these new services from Galileo, that we already have some prototypes available. We do reference products generation for orbit clocks, for ionosphere, troposphere, but also trajectories. So if you do campaigns, you need to have a reference trajectory that we can calculate. We have DNSS constellation, radio frequency simulators. We have a precise reference time at the Galileo Reference Center. We have additional monitoring platforms, for example, eMonitor that can monitor ionosphere and EVO waveforms. And we have a lot of different tools that are available. And you see some examples of the tools and outputs on the right slide. To finish this part of the presentation, so at OSPA Galileo Reference Center, we create daily, weekly, and monthly reports. So here you see an example of a monthly report that we generate. We also get the reports from the member states. We cross-check the reports. And based on this, we create monthly, but also quarterly performance reports that are becoming public through the Service Center website. So if you go to the Service Center website, you find this quarterly report for all the services of Galileo. And these are then produced by the Galileo Reference Center. So we compare it to the service definition document for each of the services. For the interface control documents, we have dedicated reports that we compare to the interface control documents, but also other services like the ionosphere. Galileo is providing ionospheric corrections, what is called the NQUIC model, and we do the assessment of the NQUIC performance. And this is also compared to a document that describes how the algorithm should work like. Okay, I will hand over my presentation to Axel, who will tell more about the HAS and OSMA performance.
Okay, yeah, thank you. So I will go quickly to the last bit of the presentation to give you up. For the HAS performance, I use material that was presented already at the navigation conference in Vienna, European Navigation Conference, the Galileo High Accuracy Service 3-year assessment of accuracy and availability. I think it's important to understand that we are monitoring specifically on the service performances, so the service contribution. For HAS, we therefore monitor specifically the quality of the corrections. So we have orbit corrections, clock corrections, and code bias corrections. And here you see for the GPS satellites and the Galileo satellites, so left side is Galileo, right side is GPS in green, Galileo in blue. The quality of the orbital accuracy of the corrections after applying the HAS corrections to the open service navigation messages. And this is an overview of 3 years. So it starts in February 23 and goes up to February 26. So you see the quality over all these months. And you can see that there is, on the Galileo side, we are quite close to the MPL target. And there has been 2 events that are exceeding. I think you need to click. There is an explanation of that in June 2024. We had a problem with one specific satellite that had an anomaly. And in May 2025, there was a specific test campaign planned that also had some effects on the HAS performance. But for the rest, the performances were quite within the targets. For GPS, you see that most of the months the performance is comparable, but we have more outliers, but also the target level that we are aiming for is more relaxed than for Galileo. For the next here, when we look at the clock, we see also that the clock corrections on the left blue for Galileo, on the right again for GPS, over all the months is quite stable, well below the NPL target. And we see that overall the corrections for GPS are a little bit less accurate. This also has to do with the stability of the clocks from Galileo are quite good. Yeah, we can move to the next slide. I can quickly go over these. It's the same slide for all the Galileo code biases. So the biases between the different frequencies, and they're all well below the target level of 50 centimeters. On the next slide, we have the same plot for the GPS satellites. You have to click through for the, yep. Finally, I have an overview of the correction availability over all the months. We can see that we are well above the targets, except for a couple of events for the GPS plus Galileo. So here on top it's Galileo only, and at the bottom it's a combination of GPS plus Galileo. And on the right you see an example of January 2026, where you see the areas that were mostly affected by the degraded or the lower performances. You can see the reason for the service exclusion zone, because that is the area where we have less coverage of the reference station collecting the measurements. So you can see the performance degradation in the over the Asia. I think that's more Thailand and lower part of China where the performance is lowest. And finally, for HAS, we have an overview of our the reference station we have here located at the GRC, where we have one of the HOUT user terminals applying the HAS corrections with the performance in the horizontal domain compared between the open service performance and the achieved HAS performance. And you can see that both horizontally and vertically there is a big improvement. Yeah, if you click further to show also the we also have a real-time monitoring tool where we can monitor in real time the availability of the corrections over time. For example, in this example, you see the two black spots is where there is no corrections available for those satellites at that moment in time. And from our member states contributions from the GMOP project that Peter already explained, we are doing analysis of the convergence time for HAS performance. In the current initial service, there is no target level defined yet, but in the next phase, when we have service level 1 and service level 2, they have a target, but we're already experimenting with the current performances to see how to define the actual point that you've reached convergence, which is round about, well, at the moment, more than half an hour to 60 minutes, but in the future, this should be reduced significantly. Then moving to OSNMA performance. So for the OSNMA service, we have 5 main KPIs defined with minimum performance level targets. It's the time between authentication for ADKD0, the MAC availability for ADKD0, and the MAC availability for the ADKD12 and ADKD4. The difference between these tags is also the latency with which they are provided regularly. And the ADKD4 is specifically for the timing component of the messages. These MPLs, they are defined on a yearly basis. And as the service is only available since since end of July, we have captured here the results from August until August 25 until May 26. And these performance targets are well met. If we zoom in a little bit on the next slide, we show the monthly values. So here we see the performance results per month, which then end up in the yearly MPL targets. but we have to recognize that these monthly performance, they are both time and location dependent. So the worst user location can be in a different location every month. So the total accumulated results for the year is usually even better than it is if you would just accumulate all the months separately. But you can see that on a monthly basis, we achieve quite good results for OSNMA on all main MPL targets. And then the last slide here is to show a little bit more detail within 1 month. So this is for the month of May. That is the last recent month, where you can see that all those performance targets, even though on a monthly value they are given very good results, we can see variations over a day. And even if we zoom in on a day, in this slide we zoom in on the 23rd of May, we can see that over a day sometimes the performances are less. So if you look at the left lower plot, we show the ADKD0, the ADKD4 and the ADKD12 authentication availabilities. You can see that at the beginning of the day there was a dip which caused the total day statistics to be affected. And on the right side at the bottom you see for the most affected metrics, the MAC availability for ADKD12 at this time, and also the OS equivalent navigation solution availability. You can see where in the world these performances were mostly affected. And usually this is in the areas where we have less coverage with uplink stations. Maybe good to mention still is that the top graph here shows the number of satellites that are connected by OSNMA continuously, because for OSNMA to work you need to have a direct link of at least 4 satellites in view to provide you enough authentication tags for all the satellites that you have in view. So if you have 4 satellites transmitting OSNMA, you should have enough satellites covered with the authentication tags in your visibility for a specific user. So that's all. I think we only have the conclusions where we can say that we are monitoring on a routinely basis all the performances of Galileo. For the high accuracy service, we already have 3 years of very good performances. And for the OSNMA, which is the last bullet, we now have already 10 months of experience with OSNMA performance, which have been very good over the last 10 months. So I hope that there are still enough people around to wrap up the session.
Thank you. There's one last question in the chat. Can you explain the picture on slide 17 regarding convergence time together with the answer in the chat by Emilio? I'm not...
The answers, what Emilio is referring to is the targets for the service level 1 and service level 2. So in the current SDD, there is no real target for the convergence time. There is a lot of experimentation done also how to determine convergence time. And this is based on the experimentation done. And it might also be the case in this particular diagram, I didn't include all the details, that this is using subsample data, so that not all that they are not sampling data on a 1 Hertz basis, but on a lower sampling.
Yeah.
So that could explain the differences here.
And this is also, well, this is an example of an experiment done by member states, and so this is not using the official HAS user algorithm.
No.
And Herbert actually saying this is probably not on 1 Hertz samples.
No.
Yes, on the service validation was made with the reference algorithm and user terminal. So the implementation could render, in fact, it does render the different results on convergence. And besides, the current applicable SDD for the initial phase is based on 68% HPA and VPE, while the final phase 1 requirements and phase 2 is based on 95%. So the accuracy targets are different. So there could be some problems in the interpretation. So in any case, this is something that needs to be improved and is improving in the current implementation of Galileo Phase 2 algorithm that I'm pleased to lead in a project by USPA.
Okay, thank you. Thank you for staying with us, and a big thank you to all presenters. It was a true technical deep dive. We will publish the recording online, so you can share it with colleagues or watch it yourselves later. Teresa, maybe you would like to give some final words?
Well, thank you very much for the webinar.
The sound is very
sorry. Now
yes,
much
it's better.
Sorry. I really appreciate the organization of the webinar, Carlin, and for both webinar, the introductory last week and this one. So we, EUSPA and GSC, and together with our colleagues from GRC, we are open. Please contact us in case you have more questions, because we were a bit short in time. Yes, and we are here to support user and to understand the user needs and requirements and to promote the adoption of Galileo. So thank you very much, also all the attendees for joining.
Perfect, thank you. There's a question about the previous webinar, and I just shared the link where you can review the webinar of last week, and then the webinar of this week will be published there as well. Thank you. Have a good evening, and goodbye.
Bye, thanks.
Bye-bye.
Bye-bye, thank you.
Thank you. Bye.
Thank you. Goodbye.
Bye-bye. Thank you.